In single variable calculus, finding a minimum is easy. Set the derivative to 0, check that the second derivative is positive, and you're done. But what if your function lives in 3 dimensions or 30? You no longer have just one second derivative. You have a whole matrix of them. Today we'll see which number to check and why linear algebra holds the answer. Let's start with what you already know from single variable calculus. Take y equals x squared. Its first derivative is 2x, which vanishes at 0, marking a critical point. The second derivative is 2, a positive number, so the curve bends upward. That's a minimum, a bowl shape. Now flip the sign. For y equals negative x squared, the second derivative is negative 2, so the curve bends downward, giving a maximum, a hill shape. The rule is simple. The first derivative being 0 locates the critical point. The sign of the second derivative tells you the shape. Concave up means a bowl, a minimum. Concave down means a hill, a maximum. Now let's climb up to two variables. A critical point of f of x and y is a place where both partial derivatives vanish at the same time. In other words, the gradient is 0. That locates the candidate point, but it doesn't tell you what type it is. It could be a minimum, a maximum, or a saddle, where the surface curves up in one direction and down in another. To classify it, we need second-order information in every direction. All of that information lives in the Hessian, a square matrix whose entries are all the second partial derivatives. For two variables, it's a 2 by 2 matrix, and it's symmetric because the mixed partials are equal. Here's the Hessian template. The top left entry is f sub xx, the second partial derivative in x. The bottom right entry is f sub yy, the second partial derivative in y. The off-diagonal entries are the mixed partial f sub xy, which appears twice because of symmetry. Let's try on the function f equals 2x squared plus 12xy plus 20y squared. First, the partial in x is 4x plus 12y. So f sub xx equals 4. Next, the partial in y is 12x plus 40y. So f sub yy equals 40. And the mixed partial f sub xy equals 12. Putting it together, the Hessian is the 2 by 2 matrix with entries 4, 12, 12, and 40. Just three numbers capture all the curvature behavior at the origin. Here's the theorem. A critical point is a minimum exactly when the Hessian is positive definite, meaning the function curves upward in every direction. The classical calculus textbook test says, check that f sub xs is positive, and check that f sub xx times f sub yy minus f sub xy squared is positive. That is literally the linear algebra test for positive definiteness. The upper left pivot is positive and the determinant is positive. Equivalently, all eigenvalues are positive. 3 views, 1 theorem. The algebra of pivots and the geometry of curvature are the same thing. Algebra is one thing, but let's see what these matrices actually look like geometrically. Take the function f equals 2x1 squared plus 12x1x2 plus 7x2 squared. Its Hessian matrix has 4 in the top left, 12 in the off diagonals, and 14 in the bottom right. Now let's check the determinant. 4 times 14 is 56. 12 squared is 144. Subtracting gives 56 minus 144, which equals negative 88. That's negative, so the determinant test fails, and this matrix is indefinite. Geometrically, that means the surface curves upward along one eigenvector direction and downward along another. The graph is a saddle. If you walk one way from the origin, you go up. And if you walk perpendicular to that, you go down. The origin is a critical point, but it is absolutely not a minimum. Now let's change just one number. Replace the 7 with 20, so our function becomes f equals 2x1 squared plus 12x1x2 plus 20x2 squared. The Hessian now reads 4, 12, 12, 40. Run the test. Upper left entry is 4, which is positive. First check passes. Determinant is 4 times 40 minus 12 squared. That's 160 minus 144, which equals 16, positive. Second check passes. Both tests pass, so the Hessian is positive definite. The surface is a true bowl, opening upward in every direction. Notice that the cross term 12 was almost the same as before, but the diagonal entry 40 was big enough to dominate it. That's the determinant condition doing its job, keeping the cross coupling from sabotaging the curvature. Now slice both surfaces horizontally at height 1, and the difference between them becomes vivid. The bowl slice is an ellipse, a closed curve with points trapped near the minimum. Its axes line up with the eigenvectors of the Hessian, and the axis lengths are 1 over the square root of each eigenvalue. The saddle slice, on the other hand, is a hyperbola, two open branches that escape off to infinity, with asymptotes pointing along the eigenvector directions. An ellipse means positive definite, a hyperbola means indefinite. The shape of the level set is the signature of the matrix. Two important warnings before we move on. First warning, having all positive entries in your matrix does not mean it is positive definite. Consider the matrix with 2 and 6 on the top row and 6 and 7 on the bottom row. Every entry is positive, yet the determinant is 2 times 7 minus 6 times 6, which is 14 minus 36, equal to negative 22. A negative determinant means the matrix is indefinite, not positive definite. Second warning, having the second partial f sub xx positive by itself is not enough either. In our saddle example, f sub xx was 4 perfectly positive, but the cross term made the determinant negative and ruined definiteness. The lesson is that both conditions matter together. It is the pivots and eigenvalues, not the raw entries, that decide whether you have a minimum, a maximum, or a saddle. So bowls and saddles aren't metaphors, they're the literal geometry of positive definiteness. This is why the concept shows up everywhere. In optimization, in machine learning loss landscapes, in physics stability problems, and in covariance matrices in statistics. Curvature in many directions collapses into a single matrix property. Linear algebra extends the simplest fact in calculus that a positive second derivative means a minimum to any number of dimensions, and that's the whole game.